The Sun. The heart of our solar system is a yellow dwarf star, a hot ball of glowing gases. Its gravity holds the solar system together. Electric currents in the Sun generate a magnetic field that is carried out through the solar system by the solar wind, a stream of electrically charged gas blowing outward from the Sun in all directions. The connections and interactions between the Sun and Earth drive space weather conditions on our planet, which can affect satellites and power grids, change the radiation belts, and trigger the aurora. And never before have we been able to study it so closely. NASA's Parker Solar Probe is diving into the Sun's atmosphere, facing brutal heat and radiation, on a mission to touch the Sun. And this spacecraft is changing the way we see and understand our nearest star. Today, NASA will reveal the surprising discoveries that this unprecedented spacecraft is uncovering about our Sun.
Hello, and welcome to NASA Science Live. This is an opportunity for you to come behind the scenes and get to know your space agency. I'm your host, Gray Hautaloma. This show is all about you being able to interact with NASA scientists and to get your questions answered. Visit us on Facebook or Twitter and ask us a question using the hashtag AskNASA, or leave a question in the comment box wherever you're watching this. Today we're taking you on a journey to touch the Sun with NASA's Parker Solar Probe. Parker is traveling through the Sun's atmosphere closer to the surface than any spacecraft before it. It faces brutal heat and radiation conditions, and it's giving us the closest observations of a star that we've ever seen. Today, we're going to share with you some of the first results from that amazing mission and explore the ways it's helping us understand our star in new ways. But before we get into the details, let's learn a little bit more about the basics of sun science.
The wind speed of a devastating Category 5 hurricane can top over 150 miles per hour, or 241 kilometers per hour. Now imagine another kind of wind with an average speed of 0.87 million miles per hour, or 1.4 million kilometers per hour. Welcome to the wind that begins in our Sun and doesn't stop until after it reaches the edge of the heliosphere, the solar wind. The corona is the Sun's inner atmosphere, the brightness that can be seen surrounding an eclipsed Sun, and home to the continually expanding solar wind. Right now, the Parker Solar Probe, a NASA mission launched in 2018, is orbiting the Sun and will get as close as 3.83 million miles, or 6.16 million kilometers, of the Sun's surface. Parker is gathering new data about the solar particles and magnetic fields that comprise the solar wind. More specifically, two of its main goals are to examine the energy that heats the corona and speeds up the solar wind, and determine the structure of the wind's magnetic fields. While many theories describe the solar wind's history, this is what we do know. The solar wind impacting Earth's magnetosphere is responsible for triggering those majestic auroras, typically seen at locations close to our north and south poles. In some cases, it can also set off space weather storms that disrupt everything from our satellites in space, to ship communications on our oceans, to power grids on land. Knowing more about the effects of the solar wind is not only important to those of us who live on Earth, it will be critical to know how to mitigate its effects once our astronauts travel back to the Moon and beyond for extended periods of time. My feeling is, if the Sun sneezes, Earth catches a cold, because we always feel the impact of what happens on the Sun thanks to the solar wind.
Well, as you saw, the Sun is very active, and all this activity influences the Earth and our entire solar system. We're 93 million miles away, and there's only so much we can see from this vantage point. But thanks to NASA's Parker Solar Probe, we're learning a lot more about our Sun up close, things you can't see from Earth. I'm joined today by Parker project scientist at the Applied Physics Laboratory in Laurel, Maryland, Noura Wafi, and Dr. Nikki Fox, head of the Heliophysics Division at NASA headquarters. So we've talked a little bit about the basics of the Sun through that video, and we're going to learn a lot more about Parker science and the great things that we're learning from it. But let's talk about a little bit about the basics. Nikki, if you could just start by, what is the Sun made of? Talk about the composition of it.
So the Sun, I like to think of it as the Sun is made of everything that you're made of. So the Sun is when it had the Big Bang, it threw out everything that actually constructed our solar system and the very fabric of life. And so we're really almost all made of stardust. The sun is predominantly hydrogen. There is helium and some other heavier ions in there. And the sun is very important to us because, of course, it's a star. And so not only are we studying the sun and finding out why it's so important to us here on Earth, but we're also for the first time really going into the atmosphere of our star.
So the sun is a glowing ball of hot gas. This gas is so hot. It's hot to the point where atoms split in negatively charged electrons and positively charged ions. And this makes what we call a plasma. And plasma, usually there is currents in it, and these currents create magnetic fields. So the sun has a hot plasma that is magnetized at the same time. And the magnetic field plays a key role in all the processes that are occurring in all the layers of the solar atmosphere. And going back to what Nikki said, 75% of the mass of the sun is protons and hydrogen, basically. The rest of it is helium. But there are traces of heavy ions, heavy elements like oxygen, carbon, iron, and others.
So the atmosphere of the sun, it is made up of all those too. Tell me about how that all relates. We think of planetary atmospheres, but what is the sun's atmosphere?
That beautiful atmosphere around the sun, we call it the corona, and of course a lot of us were really treated to an amazing show back in 2017 when we had that wonderful eclipse across America. And that's the only time that we're actually able to see the corona without using special telescopes that we build. And so that corona, it's very mysterious. It is really made of the sun's atmosphere. It is basically everything coming off the sun and being sort of held in that region around the sun. And it is one of the mysteries for us is it's actually 300 times hotter than the surface of the sun, which is just something that we need to go and study.
So there are other mysteries. Let me go back to the solar eclipse. It's really an excellent example. If you look at different solar eclipses, they look all different. Because the sun is a star, it's magnetizing, active, and it's always changing. And as such, there is so many processes that are going on that create phenomenon like the coronal heating that you talked about. But there are other ones like the breeze of protons and electrons that is continuously leaving the sun to bathe Earth and the rest of the solar system that we call the solar wind. The solar wind is accelerated to speeds ranging from 200 to 500 miles per second. And we wonder for decades, where do they get that energy from? And that's a mystery that Parker Solar Probe hopefully will help us to solve.
I know we're going to talk a lot more about the solar wind today with Parker, but tell me a little bit more about the solar wind and like what it is and how it affects the Earth and what we know about it.
So the solar wind is really very key for us. We live in the atmosphere of the sun, and so you see the corona, I mean, it's big, but it doesn't look that big when you see it during a solar eclipse. But that atmosphere is actually streaming all the way out. It bathes all of our planets on the way to the very edge of our solar system. In fact, it shapes our very place in space. So it kind of creates almost like a windsock around the whole solar system as it is orbiting around the Milky Way. And so it's really shaping it. It's the sun goes right the way to the very edge, and it interacts with interstellar space and really shields us from all of the nasty stuff that's in interstellar space. So that the solar wind is really protecting us. Now, also in the solar wind, all these particles continually streaming towards us, as Noor said, that they carry a magnetic field with them. The Earth has a magnetic field too. And so sometimes these things can interact and allow just huge amounts of energy to come into our magnetic atmosphere, our magnetosphere, causing big churning and big activity that we call space weather. And so it has a profound impact for our astronauts and also all of our technology that we rely on every day.
And that's actually why why understanding the corona is not an option for us. We need to understand it. And we have been studying the corona for years and years and years, for decades. And there are still these mysteries that we are struggling with. And the best way to prevent the devastating effects of space weather is to prevent it. And by prevent it, we have to predict this phenomenon like coronal mass ejections, like flares. And we need that basic understanding of how the solar corona works first in order to go to the second step and to predict this phenomenon.
Yeah, I think you've kind of gone over it. I guess do you have anything more to say about why it's important to understand the sun? It's very fascinating. We know a lot about it already. Why do we need to keep studying it?
So we've looked at the sun in just about every wavelength possible, and we have sent spacecraft all the way in as far as the orbit of the planet Mercury. But we've never been able to go right into this heart, this source region. And so it's like, you want to understand how a waterfall is formed. If you're at the bottom of the waterfall, you have no idea what's up there actually causing it. With Parker Solar Probe, not only are we going up the waterfall, but we're going all the way down the river to the very source, that tiny little trickle, to be able to now, for the very first time, go into that source region where all of this interesting physics is happening, where the coronal heating is happening, and where that acceleration of the solar wind. And so it is very critical that we go into this region because it's the first time that we can really get the data we need. As Noor said, we've waited decades and decades for this information. So that's why we're so excited to be here today.
All right, well, thank you so much. And we're going to talk a lot more about these things as we go through this. But we just learned, we've learned some of the fundamental science happening at our star. And why don't we hear right now from some of the leaders of this mission about what they found out in these first 4 papers that are coming out today in Nature. Let's hear from them right now.
50 years after the beginning of space exploration, we still don't understand what's heating the solar corona, accelerating the solar wind up to really high speeds.
So there's this long-standing mystery: how do you create a hot corona from a cold star?
And by going in very, very close to the sun, we're learning about the sources of energetic particles, where they begin, right down in the solar atmosphere or corona.
Well, the solar corona is the upper atmosphere of the sun. That's millions of degrees. It's very hot. Whereas the photosphere, the white light sun that you see in the sky, is cool. And so the idea of Solar Probe is to actually go there into the corona and make the measurements that are behind the plasma physics phenomena.
The Parker Solar Probe is getting so close to the sun that it will answer questions that we can't even formulate right now.
My hope is that with Solar Probe, we're finally going to get close enough to the sun, we can directly measure the solar wind in the corona.
If you're trying to study the source of a waterfall, understand the origins of a waterfall, but you're at the bottom of it and all you see is this mixed up, turbulent mess, it's really hard to understand what's happening at the top of the waterfall. And that's what we're doing now. We're getting closer and closer to the top. I think we're on the cusp of being able to answer the question of what heats the solar wind.
Figure out what physics is actually responsible for these high temperatures and the acceleration of the wind to these supersonic speeds.
WSPR has already seen some things that are giving us hints into some of the long-standing predictions of what we might see.
The instrument is working really well, and the results are very surprising.
I'm really excited that we're learning about the space radiation environment.
We now measure the magnetic field, the structure of the magnetic field. We're measuring the dynamics of the magnetic field.
We're seeing lots and lots of these small-scale eruptions from the sun.
It's very important for understanding how humans can travel or not travel out through the solar system.
So what we learned from Solar Probe will definitely play very seriously into our understanding of space weather, of the dynamics of the Earth's magnetic field, currents around the Earth that are driven by the sun itself.
It's also very important for protecting satellites in space.
To see this data, it's just a pleasure. I mean, the data is so spectacular. It's really terrific stuff.
Well, it's great to hear from the PIs. It's clear that understanding our sun can have far-reaching benefits. So now we're going to get into some of the new discoveries. Nikki, can you explain the first result from Parker that we're going to talk about today, what we found out about the solar wind?
I can do it with one word: switchbacks.
Okay.
Switchbacks. So
tell me about it.
I know, you're looking confused. So Noor mentioned that our star has a very big magnetic field in it. And, we thought that we would see a fairly laminar magnetic field. We didn't think it would be obviously just flowing out towards us, nothing too surprising. And yet when we got in close to the sun, we found these strange little features where it was literally reversing on itself and then coming back out again.
Wow. So it whipped around like at 180 degrees and... Can you demonstrate that?
You look confused. Shall I draw you a picture?
Yes.
All right, let me draw you a picture. Now, I'm pleased to say that my friends here know I'm not good at drawing, so they actually provided a sun for me. Now, you will remember from when you were at school, you sprinkled iron filings around a bar magnet and you saw a very nice pattern. Well, very similar We see that on the sun, but of course with our sun everything is complicated, so it's a little bit more detailed. But we are at solar minimum right now, so it is the least active time of the solar cycle, the least number of sunspots on the disk right now. And so that means that the magnetic field is a little bit more uniform. And so we can think of it as coming out from one side and sort of laying down as it gets pulled out, as Noor said, to sweep across all of the planets. And then the corresponding field coming in on the other side. And so you've got this sort of region here where you'd expect to see fields pointing in different directions. Okay, so we got our very first magnetic field data, and we expected when we were looking at this radial flow from the spacecraft that we would see just that magnetic field coming towards us. So you can imagine our surprise when the first thing we saw was something that looked like this. And we expected that to be a nice straight line. So the first thing we thought was, oh no, the instrument's not working. But don't worry, the instrument was working just fine. So the next thing we thought was, maybe the spacecraft is kind of in this region here, between where we would expect to see the magnetic field reversing. And as you can imagine, with the sun is rotating and nothing is simple. And so instead of this being like a nice smooth plane, it actually sort of goes up and down very much like a ballerina's skirt as she would be doing a pirouette. So we thought, okay, so maybe the spacecraft is sitting here and this whole thing is just moving up and down over the top of it. Then we added another data set to our study and realized that the material we were looking at was basically staying on the same field line. So we weren't transitioning between one region and the other. What we were actually seeing was like an S-shaped curve or a switchback in the solar wind. So we're seeing this sort of S shape. And so if I try and draw this on here now, you would see that the field is kind of doing this and then continuing out on its way, making this sort of S shape. And so it's a bit like a whip crack. So as you imagine, as you crack a whip, and you hear that sound, that is energy being released as the whip is cracking. You could also think of it as stretching a rubber band. When you stretch it and it breaks and you feel pain in your fingers, what you're actually feeling is the heat or the energy that's been released from that rubber band as it breaks. And so we think here there's energy stored in this magnetic field, and as it is straightening out, it is releasing the energy. And Noor, you had a very nice description we were talking about earlier about like a rubber hose and how, do you want to maybe talk about that?
Absolutely. Thanks, Nikki. So magnetic field is like a rubber rope. When you twist it, it will try to untwist. So having these structures all over the place in the solar corona close to the sun, it's not easy to have them there all the time. You need a lot of energy to create them. And obviously, as Nikki said, they store a lot of energy in them. And the fact, if you go back to history, historical data from space, we are used to magnetic fields wiggling a little bit. But these ones are basically flipping all the way back to the sun and out again within time scales that from seconds to a couple of minutes. And this is mind-blowing. And this, if you will, it is one of the missing puzzles that we have been looking for so long. We are actually looking for energy sources that heat and accelerate the plasma. Remember that the primary objective of the mission is to explain the coronal heating, the acceleration of the solar wind. And these structures could be one of the potential candidates that contribute significantly to the heat and acceleration of the plasma.
Certainly the smoking gun.
Yes.
And I think it's also worth pointing out that, you know, we've studied the solar wind all the way up to the planet Mercury, and we've never seen these features. So these have only become visible, if you like, to us. Now we've got inside the orbit of the planet Mercury, and we actually expect, as the mission continues and that closest approach gets closer and closer to the sun's surface, that not only will we see more of these, but we'll actually see bigger amplitude signals. And so we definitely think this is a big smoking gun today for what is causing the heating and acceleration of the solar wind.
That's amazing.
If you allow me to add just one little piece here. From 58, we have been thinking all the way that we need to send a probe there too. Mm-hmm. And actually, this structure and the discoveries that we're going to discuss, it proves just that point. Going to the source will show us the missing pieces of the coronal puzzle that we have been looking for decades now.
So the implications of these switchbacks, these new details about the solar wind, is it for prediction, for safety in the Earth, space weather area of the Earth? What are the implications of it?
So it's really understanding what's causing this acceleration. And so, if you think about it, by the time you get to the Earth, we've got this sort of smooth laminar flow. And what is causing this acceleration? And so we're seeing little signatures of this acceleration. When you add all of these signatures together, you get a big bow wave. And so for the very first time, we're starting to be able to see features in the solar wind that are telling us that the solar wind is being accelerated. Obviously, what we want to do as we get closer and closer to the sun is start to link these features to the sources on the solar surface. And once we can start to do that, then we make transformational improvements on our ability to predict the space weather that is coming towards us. So lots of great stuff here.
That's pretty amazing. We're ready to take some questions from our viewers. Reminder to everybody watching, the hashtag is AskNASA, so put that in the comment box where you're watching or use it on Twitter or Facebook. So our first Ask NASA question, I think we answered it a little. Nerva on Twitter says, have initial results given any clues as to the coronal superheating question? I think we talked about that a little. We think the switchbacks and a lot of the energy from the magnetic field around the sun is feeding these things.
Yes, and we've also seen some unexpected wave structures that we think are actually starting to excite the plasma to actually cause these switchbacks in the magnetic field. As Noor noted, if you try and twist a rubber rope, it's hard. You actually have to put some energy in there to get this feature. And so, we see these unusual wave structures, and again, we expect them to get larger and larger as we get closer to the sun. And so there are many things in this data set that are very exciting to us. But these switchbacks are certainly definitely a smoking gun, and we're looking forward to getting more information about what causes those.
That's great.
Even these switchbacks are really interesting and phenomenal. But there are periods of times where the magnetic field is so quiet and it's doing nothing. So there are no switchbacks there. But still, the plasma is loaded with energy in another form, in waves. We see a lot of waves during the quiet period where the magnetic field is steady. But once the switchbacks comes in, the waves disappear and the energy is in the switchbacks.
So there's definitely a lot of exciting stuff.
So another question about the heating issue. Maddie on Twitter wants to know, if you've never been between the corona and the surface, how do we know the corona is hotter than the surface?
That's I've got to hand this one to Noor because this is one of his favorite stories.
I love it.
Big controversy.
Exactly. So back in 1869, there was two American astronomers. They went to observe solar eclipse, and independently they observed exactly the same emission from the solar corona, what we call the green line. It's actually light in the green part of the spectrum. And that mystery lasted for 70 years. We didn't know what is the chemical element that is emitting that. In the late 1939, we actually solved that mystery. We knew that light is emitted by iron ionized 13 times. By solving that mystery, we discovered a big mystery. The fact that these highly ionized ions exist in the corona, it means the corona is extremely hot, because you cannot ionize iron 13 times without having plasma in the millions of degrees. So the corona must be extremely hot for these highly ionized ions to be there. That's how we know they are there. The corona is hot.
But for years they thought it was a whole new element. Absolutely. So actually, not too long before that, they discovered helium. Yes. Also in the same way, using these spectroscopic measurements during eclipses, they discovered helium, and they thought, we've discovered another material, yes. And they called it coronium. And that was where the controversy came. There were the group that thought it's coronium, and then there was another group that said no, it's iron, but it's so superheated that it's lost all of these electrons, and so that was how they discovered it was 300 times hotter. It's the only way it can exist.
Wow. We have time for just one quick question here. Strati from YouTube wants to know, are there correlations between the magnetic field direction and local corona temperature?
We don't know yet, actually. Probably not, but we really care more about the magnetic field direction for how it impacts us here at Earth, because obviously if it's pointing in the opposite way to the Earth's field, then just like poles repel and opposite poles attract with magnets, we get an attraction and we get an actual connection, and that allows an awful lot of energy in. So we really care about the direction of really when it gets here to Earth. It's really the magnitude, the strength of that magnetic field that I think is going to be more important.
And on the sun, as Nikki said, the direction may be important, but not that important. It's actually the complexity of the field that is important. The more complex the topology is, there is energy that is available for the plasma. When this magnetic field erupts, it transfers energy to the plasma in the form of heat and acceleration. So it's the complexity that is more important.
The more twisted it is,
exactly,
the more energy it has.
Exactly.
Well, real quickly before we go to our next segment, which is a demonstration of Parker's heat shield, I do want to know real quickly, Nikki, how it goes through this super hot area and just doesn't get
3 million degree
burned.
plasma.
Yeah.
Yes. So would you touch your stove?
Never.
Never. Good. So, you know, we talk about this 3 million degree plasma, but the plasma itself is not very dense. It's kind of a tenuous plasma. And so there aren't that many particles there. And so if you think about turning your stove on, and you set it to like 450 degrees Fahrenheit, you can put your hand inside your oven and you won't burn yourself unless you actually touch something. Now, do not try that, Gray. But if you touch something, then you actually allow that heat to couple into your fingers and you will get burned. So with Parker Solar Probe, there are not that many particles there. So even though the plasma around it is the individual particles are at a temperature of 3 million degrees, overall, there isn't that much atmosphere there to really couple into the spacecraft. So what we have to worry about is heat from the photons. I mean, we're right up by the sun. It's really bright. You put your hand near a light bulb, you'll feel that heat. And so we actually worry more about that. And so we have this incredible heat shield that still has to withstand temperatures of about 2,500 degrees Fahrenheit on the front side, whereas the instruments that sit on the main body of the spacecraft they hide in the shadow, or they live in the shadow that is created by that heat shield. And so they are at a temperature of about 85 degrees Fahrenheit, so a little bit like a Florida evening in August.
Nice. It's having a nice little sojourn, Parker is. Well, that's pretty amazing. We recently visited Betsy Congdon, Parker's lead heat shield engineer, and Jim Kinnison, Parker's mission systems engineer, at Johns Hopkins University's Applied Physics Lab, where they showed us a full-size model of Parker's heat shield, and they did a demonstration for us. So let's take a look.
Thanks, Gray. I'm here with the spare heat shield and truss structure. It is an exact replica of what's flying in space. The top heat shield is 8 feet in diameter and 4.5 inches thick. You can see that the top surface has a white coating that was specially designed for Solar Probe to reflect energy. It's a lot like being in a white car on a hot day as opposed to a black car on a hot day. You'd much rather be in the white car. The whole heat shield is sitting on a titanium frame that connected to the spacecraft, and the system keeps Parker Solar Probe at a cool 85 degrees as we approach the sun. Now I'm going to show a little demo. Hey, Jim.
Hey, Betsy.
So here we've got a cutout of the heat shield. It's the same thing, 4.5 inches thick, carbon-carbon on either side. Carbon-carbon is a lot like the graphite epoxy you find in your tennis racket or in your golf clubs, but it's just been superheated. The inside is a carbon foam. It's only about 3% dense, which is one of the reasons why it's so lightweight.
Okay.
So let's give this a try.
Okay. This isn't going to hurt, is it?
I don't think so.
Okay.
I'm going to get the front surface glowing red hot. It's not quite as hot as it's going to be at the sun. We can't quite do that. But it's pretty hot. I can certainly, even now, start feeling the heat. Jim's going to be able to touch the backside, though, with his hand.
Ready for me to try?
Yeah, let's do it.
Let's do it. Wow, that's very cool. I don't feel any heat at all coming
Nothing?
through. Nothing.
I certainly feel heat. And it's starting to get bright red on the front side here.
Nothing here.
And that is the heat shield technology that keeps Parker Solar Probe safe at the sun.
Wow, thanks, Betsy and Jim. That demonstration really puts it into perspective, the extreme conditions that Parker's battling. Our next topic deals with more science that Parker uncovered during his close flybys of the sun. We're going to head back to the Applied Physics Lab, but this time to the Parker Missions Operations Center. My friend Karen Fox is there with Eric Christian and Elaida Higginson. Karen, it looks like you're in a really interesting spot. Tell us more about where you are and the new science.
Thank you, Greg. So I am here at the Missions Operations Center at Johns Hopkins APL. This is the control center for a Parker Solar Probe. And this is where it all happens. I am here with Eric Christian, who is the Deputy Principal Investigator for the ESIS instruments on Parker, and with Aleda Higginson, who is the Deputy Project Scientist of Science Operations here at APL for Parker. Welcome.
Thank you.
Yeah, thanks. Start out. Tell us where we are. What's going on here?
So this is the Mission Operations Center, and all of the data from the spacecraft, which it sends by radio through the Deep Space Network, which is an array of antennas that NASA maintains all around the world. All of that data comes through the Deep Space Network here to the Mission Operations Center before getting distributed to the scientists around the world who are doing the real work with the science. But also all the commands to the spacecraft get sent from this Mission Operations Center. It's really the heart of the mission.
So right here, right now, this is the place where things are going up and down. We're talking to the mission. How often are you in contact with Parker Solar Probe?
So there's a few things that can interfere with our ability to talk to the spacecraft. One is the sun itself. If Parker is on the other side of the sun, then obviously that's going to interfere with communication. And the other has to do with the angle between the heat shield and the antenna that the spacecraft actually uses to talk to Earth. So when Parker gets really close to the sun, then we have to keep that heat shield pointed at the sun to protect the spacecraft, and sometimes that means that we can't point the antenna at Earth. So we go through phases of good times we can talk to the spacecraft and bad, but right now we're in a good phase, so we can talk to the spacecraft every day or every few days.
Fantastic. So we are here today to talk about the science seen by those very signals that have come down, bringing down the observations from Parker Solar Probe. So first up, tell us about this dust-free zone that we're spotting around the sun.
Yeah, so there's a dust cloud that fills the inner solar system, and it's made up of pieces of comets and asteroids. And as these pieces break off, they spiral in towards the sun, they collide with each other, they break into smaller and smaller pieces. And when they get really close to the sun, when they're very small, they either get completely vaporized by the sun, or they're so small that the pressure from the light of the sun itself is enough to push them back out away from the sun. And it's believed to create this region around the sun where there's no dust at all, or the dust-free zone. And you can actually see this dust cloud from Earth itself. It's called the zodiacal light, but you can't see the dust-free zone. And so Parker Solar Probe is diving through that dust cloud and finally getting the first hints that we might be able to detect this dust-free zone for the first time.
And there were predictions about this dust-free zone like 100 years ago, right?
That's right. In 1929, it was first predicted by Henry Russell, so it's been a long time.
It's so exciting that we are figuring out things that we've predicted from long ago. Another thing we're going to talk about today is the solar wind. This is this stream of particles flowing out from the sun that we've been talking about. And what we've learned from Parker is that it is rotating with the sun in a different way than we expected.
So the solar wind blows out in all directions from the sun. But we know that the corona, the atmosphere of the sun, rotates with the sun. It spins about every 26 days. But on Earth, the solar wind is moving straight out from the sun. So there's got to be a transition where the atmosphere of the sun goes from rotating with the sun to moving straight. The data from Parker Solar Probe shows that that transition happens further from the sun than we thought, than the theories predicted. And that's actually really interesting because this slowing down, this straightening out of the solar wind is what slows down the spin of all stars in the universe. And so as a star evolves, it tends to spin slower and slower. And the spinning affects the activity, the amount of solar space weather, the number of storms that you get from a star depends upon how fast it's spinning. So this affects the evolution of all the stars in the galaxy, all the stars in the universe, and can affect habitability of solar systems far away from our own. Really exciting.
I think it's great that we're studying our star, but we're able to find out more about the entire universe when we do that.
Yeah, so our star is our sun is the only star that we can directly go with Parker Solar Probe and measure exactly what's happening. All the others were so far away from. Telescopes can tell us a lot, but actually getting there where the action is what Parker Solar Probe is really designed to do.
Great. We're going to have one more discovery we're talking about today, more in the here and now, which is about space weather, which of course can affect astronauts and technology near Earth. And we saw with Parker the seeds of some of those space weather events. Tell us a little bit more about that.
So the ESIS instrument suite on Parker Solar Probe sees a bunch of very small solar flares. These are explosions on the sun that can accelerate particles all the way up to almost the speed of light. It's these solar energetic particles, these very fast particles, that are a danger to spacecraft and astronauts, especially when they get away from the magnetic field of the Earth, for example, going to the moon or Mars. So these are very interesting from the standpoint of space weather. And Parker has seen small events that are completely washed out by the time they get to Earth. We've never seen them before, but they form the key to understanding what's accelerating these solar energetic particles. Until we understand the basic science, we can't predict them.
All right, thank you. We are now going to take a couple of your questions from Ask NASA. The first one is from Mark on Twitter. Do we know how hot the shield got versus how hot you calculated it would get?
So we don't have temperature sensors on the front of the heat shield because they would obviously burn up. But we do have temperature sensors behind the heat shield at the back side. And then we use a model to say, okay, if we know that the front of the heat shield is this hot, then we would expect to register a certain temperature on the back side. So we've been comparing that from the first 3 orbits, and Parker Solar Probe is going to keep getting closer and closer, and we have every reason to believe that it's going to keep performing beautifully.
Fantastic. Our next question is from Ayal on Twitter, who wants to know, when the probe is on the far side of the sun, it loses all contact with Earth. How long do we have to wait until a connection is reestablished, and how unnerving is it for you?
So Parker Solar Probe encounters with the sun when they're sometimes on the other side are 10 to 15 days. So the first time Parker Solar Probe went behind the sun, we were pretty nervous because we weren't sure if we would actually see it come out the other side, but the heat shield performed beautifully, and now it's pretty routine, so we're looking forward to the next encounter.
And we have time for one more quick question on this side. This is from an 8th grade Earth Science class on Twitter. What was the biggest engineering challenge building Parker Solar Probe?
So I would think it's the heat shield. Without the heat shield, we don't have a mission. And so they put a lot of effort into proving that they could build a heat shield. They actually built a test one and ran it through these ovens to make sure that you could heat up one end and still keep the back end cool. Because without that heat shield, we just never would be able to get as close as we're getting.
Fantastic. Thank you so much. We will continue to take Ask NASA questions, a few more from this side later. And now we're passing it back to Gray Hautaloma in the studio.
All right. Thanks, Karen. That's not the last we've talked to you today either, but thank you so much. Now, Nikki and Noor, the Parker mission is unique in a lot of ways, but one of the ways it's most special is it's named for a living person, and that just doesn't happen, right?
Yeah, so it is very historic for us. It is named for Eugene Parker, and as you noted, it's not just unusual, it's actually the first time that NASA has ever named a mission for somebody during their own lifetime. And when you consider that you actually have a higher probability of winning a Nobel Prize than you do of having a NASA mission named after you, just imagine how that would feel. And of course, Gene actually joined us with his family at the launch site, and I was able to spend a lot of time with him and just really hearing just how much it meant to him. He also came and saw the spacecraft at the Applied Physics Lab before launch, obviously, and he marveled at just sheer engineering feat that was in front of him. He's very humble and gave an awful lot of credit to the engineers and the scientists who had spent all this time preparing this wonderful machine that is going to go and do the science that he really inspired a generation. He created, if you like, the heliophysics community, and he inspired the science that we do. But I bet you want to know why we picked Gene Parker, and I'm sure Noor would like to tell us.
Yeah, thanks, Nikki. So Back in 1958, a young Gene Parker wrote a paper. It's in new results, new research. He submitted it to one of these prestigious journals. And he got the review back, and the reviewer basically suggested to him to go to the library and learn more about the sun.
And that was he tells me jokingly that was his nice review. That was the good review.
Yeah.
That's great.
And obviously, but the editor was no one else but the Nobel laureate Chandrasekhar. He actually saw the value of this research. And he kept the paper for a little while, and after that he decided to publish it. And that's actually the very first seed of all theories about the solar wind. Ironically, it's not ironically, 4 years later, there was the Marina 2 mission, and a scientist named Mr.NoBuffer confirmed the existence of a solar wind. Not only confirmed it, but proved that it's way, way more complex than we ever thought. And since then, we are struggling about the mystery of the solar wind, and Parker Solar Probe hopefully will help us solve some of these mysteries.
Wow. Seeds of greatness there.
Absolutely.
So, Nikki, I know you had a chance to meet with Dr. Parker a little while ago and share some of the initial results from Parker. I bet that was really exciting.
It was. I was very lucky. I went to see him for Parker Solar Probe's first birthday on orbit. And I went to see him. We shared a lot of memories about the experiences from the launch and also seeing that mighty Delta IV heavy rocket on the pad, not only seeing that spectacular rocket, but also seeing the Parker Solar Probe logo at the very top. That was a very moving experience. And so, yes, I also got to show him a sneak peek at some of the data, and you'll see, he gets very excited about it, very emotional, and he's stayed very engaged. He's been interacting with the principal investigators and really, I think, reveling in the wonderful data that we have coming back.
That's great. That's great. Well, let's take a look at this video of Nikki's meeting with Dr. Eugene Parker.
Good to see you. Well, all I can say is, wow. And I'm not surprised that it's strange, because it usually is when you go there and make measurements. Well, I'm as excited as I expected I would be. The interplanetary space is full of activity that we really were not aware of.
And they're also very quick, so that we took images that are about 12 hours apart, and they're not there in the next image. And so they're very clear for 2 images, and then they're gone.
When you go on a space mission, you always run into mysterious things. You eventually figuring them out, but I wouldn't have expected anything like that.
And so that's the beauty of the Parker Solar Probe mission. We're going so close, and we're seeing all of this stuff for the very first time.
As usual, when you have a space mission into an unknown place, you find remarkable things that you did not anticipate. I was very moved by the fact that that spacecraft is going off into the night sky, and he'll never come back.
That's right.
Sort of sad. Your old friend.
I said I had separation anxiety. I said it was like watching a member of the team, because after working with that spacecraft for so long, she became a person and she became part of the team, and to say goodbye to her was really, really tough.
And always a little anxiety about, will something go wrong?
Yes.
And the answer is no. This baby was built to perform, and it's done its job flawlessly.
She certainly has.
Wow, it's a great video. I love how engaged he still is with the science, and
Yes.
it must be really great for you as a scientist working in the field today to be building on that legacy and be able to share it with him.
It really is. I mean, the whole heliophysics division is really just formed around studying our star and its effects on the solar system. And so everything that he did, he said, I just solved 4 equations for, he made it sound like it was nothing. And he basically gave birth to an entire physics discipline, although I always say heliophysics is the oldest discipline because everybody studied the sun since the very dawn of time. But, you know, really understanding that the sun had such a profound effect on Earth is really due to Gene Parker, and I just love the way he gets teary over saying goodbye to the spacecraft. I think we all felt like that.
That's great.
Actually, it's not only the 1958 paper. If you look at his contribution through the years, it's amazing.
Yep.
I mean, it's really well deserved that he gets named after one of the most exciting missions of NASA.
That's right.
It's really well deserved.
That's great. Well, our audience is very excited too. There's a lot of questions flowing in. Again, hashtag #AskNASA, and we'll get to as many as we can. Matt on Periscope says, have you measured the switchbacks with multiple detectors? What about at different distances from the sun?
So we did have to use, obviously, you know, that's the reason we carry all these different detectors, is we want to be able to put them together and form a full story and a full picture around the science that we're seeing. And so I noted when I drew my little sketch of the board that the first data set they looked at was the magnetic field data, but when we started adding the plasma data from the suite, which is hard to say, that was how we realized that we weren't just hopping up and down between the different regions of the sort of magnetic field, either above or below that neutral zone, but that the actual plasma was flowing in the same direction. And so the only way that could happen was for the magnetic field to continually switch back. And so yes, we do put all of the data sets together. We measured them as we went in on this orbit and saw them at this distance. As we do our subsequent Venus flybys, we'll get that little bit closer and closer each time, and that's why we're predicting that we'll actually see these switchbacks get both larger in amplitude and probably in energy as well.
Energy as well, and cadence as well.
Yes.
Yeah. So.
Well, Darren on Facebook wants to know, based on what we've seen, are we already thinking about what instruments we want on the next solar probe?
So,
maybe the director of the Heliophysics division is here. Maybe we want a string of Parker solar probes.
We'll get right on that. But actually, joking aside, that question is actually a very good question, and it really does show how NASA uses the information we get from our current missions to really build and move forward into the next generation of instruments. And so, you know, Parker Solar Probe is going to be providing these profound measurements that help us to really better predict our space weather. It will make transformational improvements in our ability to predict the space weather. And so that means the monitoring program and the information that we're going to be doing as we move forward is very, very much informed by Parker Solar Probe. So whether or not, you know, our community decides that Parker Solar Probe 2 is the thing that we should go after, whichever way that goes, we'll be building the next legacy of heliophysics missions. Will of course build on the great foundation started by Parker Solar Probe.
Realizing a mission like Parker Solar Probe after 60 years, I mean, the idea dates back to 1958, is really a big thing. Because flying close of star is not easy to achieve at all, because the smallest mistake you do, your mission is gone in no time at all. And having a spacecraft that swings by the sun 3 times and every time it comes out unscathed is so inspiring. It's not only inspiring to us as a team, but it's also inspiring to other communities as well. If you look at the heliophysics community, there are certain ideas that a few years ago we thought that are impossible to realize. Now we are considering that. People start thinking about missions that are so daring, and they will probably propose them in the near future.
I shall look forward to those proposals.
Yes. It is inspiring. Well, there are a lot more Ask NASA questions, and we're going to throw them back to the Applied Physics Lab, where Karen and her crew is going to answer them. So, Karen, over to you.
All right, hello again. We have a question from Kashnik on Twitter. Can we send the spacecraft through the switchbacks, and can we actually see them? Should I take that? Yeah. That's for you.
So Parker Solar Probe is actually flying directly through the switchbacks every time that is close to the sun. And the closer that it gets to the sun, the stronger these switchbacks get. And we can't see them in the pictures that we get back from the spacecraft, but two of the instruments that are on Parker Solar Probe, Fields and Sweep, they measure the magnetic fields and then the actual particles around the spacecraft. They're what's actually detecting the switchbacks. So in a way, we can see them.
Fantastic. Thank you. Next up is from Brandon on Twitter. If the solar wind can damage power grids on Earth and satellites in Earth's orbit, does the probe need to be protected against the solar wind when it's near the sun?
So the way the solar wind damages the power grid here on Earth is actually, it's the magnetic field that comes with the solar wind that moves the magnetic field, and that causes current to be generated in these long power lines that we use for the power grid. That can affect satellites. The things that are more damaging to satellites are the radiation, the high energy particles. And yes, Parker Solar Probe does need to be protected against that. The electronics are specially built to be able to take higher radiation than many other spacecraft.
All right, thank you very much. Next up from Manish on Twitter. What do the new findings help us understand about the sun?
So they help us understand the solar wind as it's forming near the sun. And this is important because the solar wind impacts Earth. But a lot of the things that we see in the solar wind when they get to Earth, they're very different when they're close to the sun. And so by understanding how the solar wind is actually formed and why the corona is so hot, we're hoping to be able to better understand the environment around Earth itself.
Great. Next up is one we definitely get a lot, which is from Kashik on Twitter. Does Parker Solar Probe take pictures of the sun?
So Parker Solar Probe actually has two cameras, but they can't take pictures of the sun itself. We're getting so close that the sun would burn out any camera that we could make. But what we are taking pictures of is the corona, the atmosphere of the sun, off to the side. And that shows us the streamers that we see coming off the sun, the solar wind we see coming off the sun. And so we can see a lot of the structures that we're about to fly through because the two cameras are on the front end of the spacecraft. And so they're extremely useful and scientifically interesting. But taking a picture of the sun at closest approach, just we can't do.
All right. Rami on Facebook asks, how long is the mission altogether with planning, travel time, and observation?
So Parker Solar Probe is a mission that's actually been planned for more than 50 years. We've known about the mysteries of the sun and we've wanted to go there and find out what the answers were, but we just didn't have the technology. And the spacecraft itself actually launched in 2018 and it's going to go through 2025, so that's 7 years. It's going to do 7 flybys of Venus and 24 orbits around the sun.
Great. We have a question that I'm going to ask each of you to answer, which is from an 8th grade Earth Science class on Twitter. And they want to know, what is the biggest scientific mystery you want to solve with Parker Solar Probe? So Eric, you take it first.
So the instruments that I work on study the energetic particles that come off the sun, moving at almost the speed of light. After all these years of studying them, we still don't know exactly what accelerates them. And yet these are the particles that can be damaging to spacecraft and even astronauts in orbit. So understanding the acceleration, how you get these pieces of atoms moving up to almost the speed of light, is really what I'm interested in solving with Parker Solar Probe.
I'm going to give Aleda one chance to answer too.
Sure. So I study the solar wind, so I'm most interested in the Sweep and Fields instruments, which study the actual particles in the solar wind and the magnetic fields. So we're really hoping to understand the origins of the solar wind, how it's escaping from the sun, and then how it evolves as it moves towards Earth.
Fantastic. Thank you guys so much. We are going to go back to Gray Hataloma in the studio. Thank you so much.
Thank you.
All right. Thanks, Karen. So we just discussed a lot of exciting science about our sun, and that discussion is only beginning. The science can help us understand not only the environment in our own solar system, which is driven by the sun, but also help us better understand the science of other stars in the universe. Let's watch a quick recap of all the science we just learned about.
For the first time ever, we were able to go to the source of the solar wind and solar particles. Here are 5 features Parker saw. We've long known that space is full of cosmic dust. We can even see the dust from Earth because it reflects sunlight. Parker saw evidence that the dust stops at an estimated 3.5 million miles from the Sun. As the dust gets closer, the Sun vaporizes it, creating a dust-free zone surrounding the star. At Earth, it appears that the magnetic field lines flow evenly out from the Sun, but Parker saw them behave in a surprising way. The magnetic field lines flip in a whip-like motion, turning 180 degrees around in a matter of seconds. These switchbacks came in clusters and were timed with fast-moving clumps of plasma in the solar wind. Scientists have long wondered if the solar wind is generated as a continuous flow or in spurts. We now see evidence that the solar wind has rough, irregular texture. The plasma within it also seems to lack an orderly sense of direction. Some clumps of solar material fire out into space, while others fall back toward the Sun. These clumps may be distorting the magnetic field, causing the switchbacks. They may also be an indicator of what the solar wind looks like in its early stages after its birth on the Sun. Parker found a transition point in the solar wind. The corona is the Sun's faint, outermost layer that transitions to the solar wind. Before Parker, scientists knew that the corona rotates with the visible surface below it, but they didn't know how, or where, the solar wind switched to flowing straight by the time it reaches Earth. Parker has finally spotted signs of this transition, and the changeover happened significantly farther out than expected. Although the Sun has been very quiet over the first two orbits, Parker observed several tiny bursts of solar energetic particles. While these events have been seen before, never ones this small. The fast-moving particles from these modest bursts spread out as they move from the Sun, making them undetectable from Earth. Without Parker's front row seat, we would never know that the Sun is regularly producing these small-scale events. Fast-moving particles are a source of dangerous radiation. The more we learn about these eruptions, the better we can protect our technology and astronauts. Parker still has more work to do, but it's already helping us see our star in a whole new light.
Well, that's all the time we have today. I want to thank you so much for joining us, Nikki and Noor, and ask you to just give us a couple of real quick final thoughts on this wonderful mission.
Well, from the data we got so far, Parker Solar Probe showed us a new picture of the solar corona. There are so many surprises. If there is one thing that we are certain of going forward, is that we will never see the solar wind the same way we've seen it for the last 60 years. Parker Solar Probe will rewrite the textbooks for us.
Mm-hmm. And I would just say that Parker Solar Probe is certainly holding up being the coolest, hottest mission under the sun. We're excited by all of the results that we have seen, some today, and of course, this is just the start. These are the first 4 big papers, but we have a lot more science to do. Upcoming, our next Venus flyby, December 26th, when we'll actually go yet closer to the sun with those next couple of orbits, and then another Venus flyby, and in we keep going. And so, you know, for the NASA Heliophysics Division, we are just so excited about welcoming Parker Solar Probe into our fleet, getting this incredible data from the first time in this key region, and of course using these data to support our Artemis mission as we go forward to the moon, to Mars, and beyond.
Well, again, thank you to you both, and thank all of you for watching. And continue sending us your questions about Parker using the hashtag AskNASA. We're going to make a special video that will answer them. It's going to be posted to the NASA social media pages, so keep a lookout for that. Plus, join Parker experts again tomorrow during a Reddit AMA at 2 p.m. Eastern, and more results will be revealed next week at a scientific gathering known as the AGU. Thanks so much for joining us. Until next time, don't look at the sun, but keep watching it.